But those are interesting applications. Maybe you will also like what I'm going to present today.
Yeah, sure. That is the reason myself and my students also joined there.
Okay.
Thank you, Shobhushaji, for sending the link.
Most welcome, sir.
Maybe I can also learn from you and also from your students.
Sure.
Rajdeep, let us start. I think it will be.
Yeah.
It's already 6:09, so let us start.
Yeah.
Let us start.
Okay. So, hello everyone. So, welcome to the fourth webinar of IEEE Computer Society. So, Kharagpur section. So, so myself, Rajdeep Ghosh, I am the secretary of this core section of this Computer Society. So today with us we have Mr. Sandeep Batula. So he's the co-founder of Qvilium Technologies Private Limited. So he will be presenting today on a talk on the topic of from sensors to insights, the power of edge computing in industrial settings. So welcome, Sandeep sir.
Thank you so much.
So just before we start, so let's have a small introduction on sir about his workings and everything. So to start off, his professional background. So Mr. Sandeep Batula is the co-founder and the visionary leader of Qvilium Technologies Private Limited, a pioneering fabless semiconductor design company based in India. So as a renowned expert in edge computing and silicon photonics, he's revolutionizing the field of real-time data processing and analytics for industrial and environmental monitoring applications. To gist of his achievements, Mr. Batula's recent achievements include the design and development of edge computing solutions for industrial process monitoring and autonomous underwater vehicles, utilizing the digital twin technology and multi-sensors data fusion. Mr. Batula's outstanding contribution to sustainable innovation has been one of the recognized things globally. So he is also a recipient and of the prestigious Leaders in Innovation Fellowship LIF Global Award by the Royal Academy of Engineering, UK. His future works mainly in Qvilium Technologies includes the development of edge computing solutions for space-based applications, leveraging his expertise in silicon photonics and on chip laser design. So a short notice to our attendees also. So kindly keep yourself muted during the talk session. So if you can wait till the end for any questions or anything you want to ask Mr. Sandeep Batula. So in case you have any doubt, you can just list down your doubts in the chat box itself, in the Google Meet chat box, as well as in the YouTube live stream. And attendance sheet will be soon distributed to you. So kindly fill out your attendance thereafter. As I said, you may type your query or issue in the chat box directly. Also, at the end, we will be taking a small group screenshot of the event. So kindly, if it's possible, please turn on your camera at the end when we are asked to do so. So yeah, that was from my end. So I guess Sandeep sir, you can start from your end.
Yes. Thank you so much, Rajdeep, for such a quite nice introduction and setting up the stage for the further conversation. Let me pull up my screen. I think it is visible. And I'm
yes, sir, it's visible. Sir.
Yeah, thank you so much, everyone, and thanks for joining today. And first, I would like to thank the IEEE student chapter from IIT Kharagpur CS department for inviting me to such an insightful talk on edge computing and its use cases in industrial applications. So before directly jumping into the presentation, let me tell you something. So imagine a world where the drones are able to capture the data from the fields and provide the waters to the plants, which is only needed the water, and remaining plants, they don't spray the water on it. And also imagine the autonomous underwater vehicles, which are exploring the depths of the ocean, be able to take its own decisions without relying on human interventions or human inputs. And this is not only the one of the use case. Now also imagine to the air quality monitoring or emission monitoring in industries, where there is a lot of chances of gas leaks from the industrial pipelines. Now just imagine there is a network of sensors which can process the data at the edge without depending upon the cloud for ML processing or data processing. So these are just a few examples where we can harness the power of edge computing in the real-time environment. So the future is now coming. So edge computing is a buzzing word. So today in this talk, I will be mostly focusing on the applications because as an industry, we always love to explore the applications and use the technology as an indicator and also reminder for these other use cases. So today I'll be talking about the farmlands, the ocean floors, and also to the industrial pipeline detection. So before that, let me introduce myself. My name is Sandeep, and I'm the co-founder of Qualivan Technologies Private Limited. And we are based out in KIT University from Bhubaneswar, if you are familiar with this university. And we have also been supported by Royal Academy of Engineering from UK for our sustainable grant management systems. And we are a fabless semiconductor startup who are currently manufacturing advanced photonic sensors, mostly for environmental monitoring applications. For example, gas leakages or emission monitoring from industries. And we're also parallelly exploring other applications, for example, medtech, and also in terms of drone-based applications for UAV monitoring of data. So this is it's a short discussion, short introduction about our company. And this is our team, stellar team, which I cannot resist to introduce to you, like Pawan, Shantosh, Sandeep, and Kishore. So we are the four team who are currently managing the whole company from technical point of view, from the marketing point of view. And we also, on the other side of the coin, we also have the great advisory board, all the way from UK, India, and also from the scientific advisory from IIT Madras, who is Chandan Sarangi. He is the civil engineer and also, sorry, he is the assistant professor from civil engineering from IIT Madras. So with this set of team and advisory board, we are not only exploring the potential applications in the national level, but we also placed our in very various international levels to understand the applications and provide the customized solutions for them as a sensor, as a service. Well, our journey started in 2020 with the IIIT Hyderabad, and later on we have been incubated at ISA Bangalore, and we got a fund from ISA Bangalore to develop the first sensors using the technology called silicon photonics that I will be explaining in the coming slides. And currently we are shifted to Bhubaneswar because we found Odisha is a place for manufacturing, from drones, from biotech, from medtech, and all the way to sensor technologies, also in terms of semiconductors. So this is the short journey of our company. And the sensors that we are currently developing is called silicon photonics. So silicon photonics is just like edge computing, which is currently, getting growth in terms of the market. So the silicon photonics is just like optics. So we have a basic understanding of optics from our 12th class physics or 10th class physics. What are the optical systems that you can see? Those are very bulky in nature, right? You can see most of the equipment will take a space on the benches, and you cannot move outside to do the testing. So we can assume the silicon photonics technologies as a lab on a chip. That means we can fit all these optical components, like big optical components at the size of a CPU, all the way to the size of a rice grain inside a chip. That is the most beautiful advantage of using silicon photonics. That means now we can not only integrate everything on a chip, we can also reduce the cost, power, and now we can do real-time monitoring, which is not possible previously. So this is the advantage of our technology, and we mostly use this technology and also chips for meteorological parameter sensing, for example, temperature, humidity, and also advanced sensing applications like for gas monitoring. We can monitor multiple gases like CO2, carbon monoxide, hydrogen, everything within a single chip, it depending upon our use cases and our industrial client use cases. And this is the chip that we developed, and you can see this is acting as a miniaturized spectrometer, and this is the chip that we developed as a packaged version. Let me use my laser pointer. Cool. And these are some of the nanostructures. So in silicon photonics, we mostly talk in terms of nano level, just like the Ant-Man. So everything that is fabricated is at a very nano scale, which we cannot see with our human eyes. It's only be possible to see with the electron microscopes, scanning electron microscopes. And the benefits, just like electronic integrated circuits, which is very mature because that has been since from 1960s. Currently, the photonic integrated circuits are taking a new age. So they're making a dent in the universe by integrating all these optical components, which can be customized to fit in a single chip. So in the near future, I can say by 2030, most of our computers will be having not the microprocessors, but the optical processors. So this is the dent that it is creating in the coming future. And one of the advantages, it can be easily mass deployable. That means we can scale it up to include a mass deployment kind of environment. And also it requires very less power to operate. It barely requires 10 milliwatts to 10 milliwatts of power to operate. It's a very battery intensive, not a battery intensive stuff. And this is our developer chips. We started with the Vajra P1, Vajra P2, and Vajra A1. So Vajra P1 is basically we developed for ammonia gas sensing, and Vajra P2 is for multiple gas sensing like CO2, ammonia, NO2, etc. And it can also be operated in the water environment. And the Vajra A1, which is a very much advanced version that includes all the lasers and detectors which is sitting side by side in a single chip. That means when we compare Vajra P1 and P2, they don't have any sources and detectors right on the chip. But at Vajra A1, we have all the lasers and detectors. Like you cannot believe that this chip has around 7 lasers and around 7 photodetectors, which can be packed in a very small size of 5 mm into 5 mm of diameter. So this is very small in size. We can easily fit into wearable applications or drone-based applications. Like we can replace the bulky systems and replace the bulky systems with these miniaturized systems. That is what our intention at Polygon. And these are few of our applications. We mostly focus on environmental monitoring and microplastic detection, which is a very buzzing word. Microplastics are everywhere now. We can even find the microplastics in our brain, in our placenta of baby, in the baby as well. And aviation sector and also biosensing. So these are few of the applications. And now coming to the topic. So you might be wondering, like most of our work is almost engaged in terms of designing photonic ICs. But where do we actually involve in edge computing? So this is the question that we asked ourselves in our team, because without edge computing, we cannot process the data from the sensors. You can take any sensor, they can provide very redundancy in terms of data. In order to filter out the data, we must require some tool to achieve that. And that is what edge computing is. So this is the quick outline of the presentation today that I will be delivering, where I will be starting initially about edge computing for industries, why it is required, and some of the use cases of edge computing. And as a company, as a startup, we always, depending upon the third-party providers, for example, AWS Greengrass IoT architecture. So I will be mostly going through the AWS Greengrass IoT along with these architectures. And finally, I will be providing 3 use cases. One is the digital twin of autonomous underwater vehicle by using edge computing, and precision agriculture using edge IoT. And finally, we are including ML as an inference. It is especially for detecting plastics in the oceans. So these are the projects. That we developed with a collaboration from few universities from Andhra Pradesh, because we are situated near to Andhra Pradesh at our Odisha border. And finally, I will be explaining about our ongoing work with silicon photonic sensors, how we are integrating the silicon photonic sensors for efficient data monitoring, and also to the edge computing or edge IoT for industrial setting. That will be mostly, I'll be talking about gas leak detection systems for industrial pipelines. Yeah. Now, well, you might already familiar with the edge computing. Why should we use edge computing regardless of cloud? So you already know that cloud is not efficient in terms of data processing, because especially when the cases where latency is involved. So it is like some cases there is like fire on a hair problem. For example, you can take remote operations. The doctor is sitting in the ES and he's performing operation in India. So every movement that he's performing at the ES, it must be latency free, and whatever he is moving in terms of robotic arms, it must be very instantaneous on the other end. So if you depending upon the cloud, because of the latency involved, you need to send the data to the cloud, and it will take some time for the cloud to process the data and get back data to the real system. So this latency is a very issue in terms of cloud. And that is where we are using edge as an alternative option, where we are bringing the cloud processing all the way to the place where the data is generated. Now we are moving the intelligence from the cloud to the edge. That means it can process all the information at a very real speed without depending upon the cloud infrastructure. And also it can increase the bandwidth requirements, because if you see industrial settings, if you go to any industry, they're generating around terabytes of data daily. And it is very impossible for the cloud environment to process the data, because we need to filter out the redundancy data from the sensors and do the edge computing capabilities. So this is the power of edge computing. That is the reason most of the companies and industries are also now trying to shift from the cloud to the edge to harness its power. Well, the use cases, there are a lot of use cases, not only few, we can say thousands of use cases, but because of the time constraints and in this presentation, I'll be talking mostly on these 4 use cases, like the one that we're developing, digital twins, IoT in agriculture, and edge plastic identification. Now, we also know what are the challenges in the industrial IoT environment. If you go to any industry, they are placing the sensors in a place where there is no internet connectivity. So there is, intermittent connectivity issues and also power and size limitations. And most of the sensors in the industries are heterogeneous. So they bought the sensors from different manufacturers. So each sensor is generating different kinds of data formats. And it is very difficult for, cloud-based computing to discriminate and differentiate the data coming from heterogeneous sensors. So this is a very big problem for the industries, and also integration is also a challenge because if you depend upon third-party cloud vendors, industries don't actually trust these cloud partners because their data is very sensitive and they don't want their data to be exposed to the outer environments. So there is a strict regulations for the industries in terms of integrating their servers with the cloud computing. So all these are the challenges that industrial IoT environments are facing. Now, so before going directly into the edge computing, let me tell you why I'm talking about silicon photonics, what exactly it is. Well, so let me compare the sensors with the optical fibers because the internet that we are getting daily in terms of optical fibers. If you take any optical fiber, it consists of the core. The core is the main thing that can carry the light from point A to the point B or source to the destination, and it is called clad. Photonics is. So in silicon photonics, you can imagine the core, which is a glass in terms of optical fiber. Now we are depositing this core as a silicon, just like a waveguide. Here you can see. The silicon is acting like a carrying information from source to the destination, and silicon dioxide is a cladding material. So just like the glass in terms of optical fibers. So that means we can use these chips anywhere, not only in terms of sensing, but it can also be useful for quantum computing and also data centers. And one of the the beauty of this technology is you can also integrate the detectors. Here you can see. So this is the silicon, which is just like the core, and this is the germanium detector, which can detect the signals which is coming from the sensing part, and you can directly transfer the signals to electrical counterpart. So if you see recently, the NVIDIA has launched Spectrum X, which is powered by silicon photonics technology. And by using the silicon photonics technology, you can reduce energy intensive tasks, and you can also speed up the processes at a very higher speeds. They're talking about terabits per second, or that's that much of speed. So there are a lot of advantages by using silicon photonics as the core structures. And just give you a size comparison, how small that we are talking about in terms of silicon photonics. Let us take the diameter of human hair. So it is around 75 micrometers. Now we are talking about the silicon photonics waveguides. That means the one that is carrying the light, which is at a diameter of 500 to 800 nanometers, not even 1 micrometer. That means we are talking about 75 times smaller than the diameter of human hair. So even though those are very small, these can be useful for many applications at a very high speed. Also, you can also include as a data sources. And this is the technology that we are developing at Quali1. And now with the basics of what silicon photonics is in, now let me introduce AWS IoT Greengrass, which is a service provided by Amazon Web Services as a part of edge computing. Well, in edge computing, if you see, this is the cloud environment. There is a service called software, I can say, called Greengrass IoT. So this can be deployed at the places where we want to actually process the data. For example, this is the industrial environment where there are a lot of sensors which are connected to the industries, processing the data, gathering the data, and providing the data to the cloud. Now, instead of directly sending the data to the cloud, we can deploy this edgelet, we can say edgelet, to the place where it is generating the data. And now the data can be redirected to this edge environment to process the data. So this is the basic architecture what Amazon AWS has provided. And this is the overall architecture of what is happening inside the cloud. So we have the AWS cloud, VPC, EC2 instances. All these are the server architectures. Now, this is the instrument that we want to monitor. And we can also use OPC-EA. This is very much useful or important for the industries because industries don't rely on MQTT. They only rely on OPC-UA or Open Protocol Unified Architecture call. So this is very much compatible for the industries. That means by using edge computing from AWS, they're also providing these connectivity options for the industries. For example, few industries are opting OPCA survey and few are opting Modbus. And for consumer level applications, we can use TCP or any other MQTT services as an option. So that is the advantage of using this AWS Green Dash service. Now, let me directly go to the case study, which we developed as a part of one of the collaboration with the university, which is the digital twin of autonomous underwater vehicles. But why should we use digital twin for AUVs? Well, the problem is most of the AUVs, if you see autonomous underwater vehicles, if you are involved in any kind of marine activities, so these AUVs are deployed by naval researchers and also oceanographers to study the state of the ocean. Not at the higher depths, they can deploy these AUVs at a depth of around 50 meters to 100 meters to study the state of the environment. For example, what is the temperature, how the pollutants are affecting the ocean currents. All this can be studied using these AUVs. Now, one of the biggest problem for the AU deployment is they are not only operational intensive and capital intensive to deploy, but once you deploy the AUV, once it enters into the ocean, whatever the communication you have with the autonomous underwater vehicles will eventually cut down. That means it is now navigating itself. Whatever the code that we written when we are doing everything in the terrestrial environments, it needs to navigate, it needs to process the data. And once it is done with its task, it needs to get up into the ocean surface. But the problem is sometimes the AUVs might lost because of lack of information and lack of communication, I can say. And there are few cases because the building of AUV is a capital intensive task. It will require around crores of amounts of money to build the AUV, and it is very painful to see that your AUV is sinking into the ocean or rivers, whatever it may be. So we need to establish there is a solution we require to establish the communication once the AUVs enter deep into the ocean. So how do you do that? Well, we proposed an idea like there is something called autonomous surface vehicle that is parallelly going along with the AUV. That means AUV is doing some exploration underwater. Now parallelly it is communicating with the AUV in terms of acoustic link. So here we are using acoustic links because in underwater environment, you already know that we cannot use any form of communication except acoustics. So this is the communication that we deploy. We can call it as hydrophones. We can use hydrophones to acoustically send the signals from AUV to ASV and vice versa. And this ASV is connected to RF link. That means whatever the information that it is getting from the AUV, for example, its battery power or whatever the anomaly is that is AUV is facing, everything to the terrestrial environment in which the operator is sitting. So in this manner, we can provide real-time information, real-time health monitoring system of this AUV. Now, so this is the overall architecture. So see here, there is an AUV which is doing operations inside the water, and there is ASV which is running parallel or in sync with the AUV by adjusting its path and direction. And this is directly giving the information through radio link to the user who is sitting at the terrestrial environment. So now this user is directly connected to the AWS Green Dash because in AWS Green Dash, initially we use the cloud services from AWS and we deploy this AWS services or Green Dash service to the edge computing or edge device. For example, here we are using something called Raspberry Pi, and this Raspberry Pi has now the edge computing software, and that is directly linked to AWS IoT. Now, whatever the information that we are getting from the AUV will be directly going to AWS IoT server, and from here we can connect to various other services from AWS. For example, it will directly go to Green Dash, and from Green Dash we can put something called connectors. From these connectors, we can directly connect to AWS IoT Twin Maker, which is useful for creating digital twins. And we can also use something called Grafana service, which is useful for creating some kind of visuals. For example, whatever the health parameters that we are getting from the AUV, that can be visualized in terms of real-time visualization in our data, in our dashboard. And we can also use AWS SSO single sign-on and identity access management for creating users who can actually access the data. So this is the very small architecture, but there are a lot of background work which is going on when we are talking in terms of coding and everything. So this is the basic architecture on how we can get the data from the AUV and monitor the data in the real-time dashboard. And this is the hardware description where, So here you can see this is the ASV, autonomous surface vehicle, and this is the AUV that we have developed. And this consists of Raspberry Pi, And this Raspberry Pi here you can see, which is sitting on the terrestrial environment. So which is at the operator environment, and the ASV has its own Raspberry Pi, which is useful to gather the data from the ASV. So here it is connected through wired connection because we haven't developed hydrophones because of expensive nature. So we have done a POC kind of model using wired communication. Now let me play the video. Yes. Oh, sorry. Yeah. So we have done this testing at the nearby swimming pool, and now you can see the AUV sinking inside the water. And this is the dashboard that we created. Like we have some visualizations here, for example, humidity, temperature, and also some of the health parameters that we included later. Yeah. So whenever we deploy the AUV, it is directly connected to the ASV through wired link, but we can also make it wireless if you want to deploy the AUV in the shallow water region, because in shallow water region we cannot directly depend upon the wired communication. So we can use hydrophones for this purpose. And whatever the data we got from the AUV can be directly synced to AWS digital twin in the dashboard. So we can have some kind of sign-in options. Now we can see its humidity, its temperature, because these are very important parameters inside the AUV. If temperature increases by any short circuits in the batteries or any electronics, we can easily command the AUV to come back to the surface in order to save the disaster. So this is one of the use case, and the case to study is about precision agriculture using edge IoT. And this is the overall architecture. So in this project, we deployed some field sensors, for example, the humidity sensors, soil sensors, and temperature sensors. And now it is connected to the OPC server. So this OPC protocol is actually very useful to identify the offline data, and it can also be able to sync directly to the AWS environment, which is very useful for the industries who want to opt OPC UA as a service. So here again, we deployed Raspberry Pi, the one that I showed in the AUV kind of use case. So we deployed the Raspberry Pi with a lot of connections to the sensors, for example, humidity sensor, real-time temperature sensor, and also cameras. And this can be useful for identifying any kind of animal interventions in the fields. So this can be directly send the data to the AWS Greengrass core. And there is a service called Lambda that can be deployed from the AWS Greengrass environment that can take the local decisions using inference models. So initially we trained the model in the cloud environment, the basic model in the cloud environment, and we deployed the trained model as an inference to this AWS Greengrass code, which is in our case is a Raspberry Pi, the hardware which is running the AWS core. Now it is getting the data, processing the data, and sending the trained data again back to the AWS. So this is the overall architecture that we developed in terms of precision agriculture. And this is the IoT dashboard, and this is the OPC UA server. Here you can see the data which is spitting from the OPC UA along with the timestamps. So this, let me use the pointer. Yes. And these are the deployments that we have done using AWS IoT Greengrass. We were using version 1, but I think now they have moved it to version 2, which is much more easier to deploy. And this is the dashboard that we got from the different sensors into the AWS environment. And so far we talked about the digital twin and also precision agriculture. And now we can also include ML inferences. We have used this project for ocean plastic monitoring. So this is one of the advanced project that we proposed to one of the IEEE project, in which we have used the AWS IoT service as usual, but now we are using something called WiMAX receiver, because in our AWS AU use case, for example, here you can see we depending upon radio link, which is not much efficient because sometimes it requires line of sight and sometimes it get distributed because of some other reasons. So this radio link does not becomes very efficient in terms of oceanic environments. The alternative option is we can depend upon satellite communication, but that is much more expensive. Satellite communication is much more expensive. So we are using something called WiMAX receiver, which is a hardware device, and that can be easily deployable in the oceanic environments, and it can cover the distance up to 100 kilometers to 200 kilometers. This is very efficient in terms of data transfer. So in this case, now we can directly deploy the greengrass core into the oceanic environment, in which previously we depending upon the terrestrial user, because in our previous case the AWS greengrass core was sitting at the terrestrial, not at the AUV or ASV level. It is not in the ocean. But in this case, we can directly deploy the AWS greengrass core or edge computing software directly to the oceanic environment, and we can directly get the data to the AWS IoT core or AWS IoT environment. But one of the one of the disadvantages of this WiMAX receiver is we require something called WiMAX base station. This must be very nearer to the ocean environment, or something nearer to the ocean shore, in which otherwise this technology does not able to work. So this is what currently, if you see in recently we went to UK, so they are developing this WiMAX technology in order to improve the edge computing capabilities. And this is the architecture. And in this case, since we directly deployed the AWS greengrass into the oceanic environment using WiMAX gateway, so here we can use the cameras, or we can say Raspberry Pi cameras, to identify the floating plastics which are on the surface of the ocean. They are continuously traveling. So the main motivation of this project is we can use something called buoys. Buoys are the very static structures that can be sitting on the surface of ocean, and they're anchored to the ocean floor, so they cannot move even with the currents of the oceans. So these buoys are able to detect the microplastics, or sorry, not microplastics, but the plastics which are floating on the surface of the ocean. So the main motivation is we want to identify, for example, if you deploy these buoys in Chennai, Chennai beaches, or in the Visakhapatnam beach areas, you can find which city is actually emitting more amounts of plastics into the ocean. So this is one of the greatest use case, because in terms of air quality monitoring, we can map, emissions. You can say today the AQI is very poor, and tomorrow its AQI is severe or good. So we can map because we have the data related to the air quality information. But in terms of ocean plastic, we don't have any data. So the motivation of this project is to map the ocean plastics and say, okay, this region has this much of plastics, and this region has this much of plastics. So in this manner, we can, stress the governments to make some policy making decisions to stop the plastics right away from the source. And we can also use this AWS edge computing service to achieve that purpose. So here we deployed everything at the oceanic environment, and we are using here something called object classifiers that we already trained using AWS SageMaker in AWS Cloud. So once we trained and we got this inference model, and we directly deployed this inference model to the edge computing, just like the one we deployed in our previous precision agriculture use case. So here we can also use so many services from the AWS. We can club so many services to do, for example, real-time alert systems using Amazon pinpoint service. Here we are not including any pinpoint service, but we can also include the emailing services or SMS services, alert services to the government to see what kind of plastics that they are getting from the oceans. So this is one of the use case where we can directly deploy ML models into our core systems like AWS greengrass core in terms of hardware systems. Well, now finally, I would like to say our ongoing work with silicon photonic sensors for industrial edge asset monitoring, or also we can use it for distributed acoustic sensing. Usually, if you see the gas pipelines, which are already deployed in our country, so they're deployed around, if you take an example of BPCL, Bharat Petrol Coal, BPCL and Indian Oil, they already deployed around 2,000 kilometers to 4,000 kilometers of these pipelines throughout India. But one of the challenging tasks for them to monitor the gas leaks from these pipelines. So they're using something called distributed acoustic sensing, but this is very much expensive and it requires a lot of resources to be deployed. So in this case, we are developing something called silicon photonic interrogators. That means we can deploy the sensors all the way along the pipelines in order to monitor whether there are any gas leaks. Now, in order to achieve this, we require some kind of intelligence, because if you deploy such huge amount of sensors, they can generate a lot of data continuously 24/7. So we need to, sometimes they also provide redundant data. Now we require some tools to filter out this redundant data and also decrease the amount of data that can be processed. That means now we are closely working with edge computing capabilities because we had an experience on working AWS Greengrass. Now we are also working some other alternative technologies, other alternative tools to deploy these edge computing services as well by using local ML inferences or data filtering. So this is what we are currently working on closely with BPCL. And yes, so this is the architecture that we are currently planned, but it requires some approval from the BPCL. Maybe in the next few months we'll be having some discussion with the BPCL for deploying our sensors and also finding out which service that can be useful for in this edge computing environment. So with this, I would like to thank everyone for your attention, and thank you so much for this opportunity as I have covered everything in the application perspective. And I would also like to explore whatever the thoughts that you have in terms of using edge computing efficiently, especially for industrial use cases is concerned. Thank you very much. And now I am open to any questions and discussions if you have.
Thank you, sir. So I guess already we have 2 raised hands. So yeah, Aditya, you can.
Oh, sorry.
Yeah, very nice presentation of yours, sir. Thank you for your presentation. I have a small doubt. Yeah, as you shown about the AOV.
Yes.
So,
Yes.
what is the depth of that AOV can go?
Usually AUVs go with a depth of 50 meters, because if you increase the depth to the AUV because of the oceanic pressures, the hull of the AUV.
I understood. What
Yes.
is your model can go? Up to what extent your model
It
can
can
go?
go up to 10 meters because we haven't designed by considering material as a perspective. It was just like a POC we developed with the basic structures. So
Fine.
we tested at only 10 meters of distance.
So all the 10 meters that wire will go between AUV and ASV?
Yes, that is a wide communication, and because when we were working with the university, we were proposing them to use hydrophones, but because of the budget constraints, they settled down to using wide communication, or we can call it as threaded communication for the purpose.
Okay. So is it an autonomous wire or we need
Yes,
to
that is autonomous. So whatever the code that they deployed, it is completely autonomous because the professor that I worked, he already done some kind of project with the Indian Navy of around 100 crores, in which he was the main contributor in terms of deploying the AUV. If you remember the pictures that I showed in terms of problem statement of AUV, that was the whole system he developed. But now he is looking for the solution of integrating that with edge computing.
Fine, thank you.
Yes.
Yeah, next, Srinivasan, you had some doubt. You can just unmute and ask the question.
Good evening, sir. Sir, it's a nice presentation. Sir, I have a few queries. The query number 1 is that this ASV and AUV is connected with the theta.
Yes. It
Sir,
is
and I have seen you have checked your AUV in the pool, swimming pool.
Yes,
Did
yes.
you try it in ocean?
Oh, not yet, because if you want to try it in the ocean, it requires a lot of things to be considered. First of all, oceanic environment is not steady, right? You already know it is prone to a lot of challenges. That was a kind of POC we developed.
Exactly, sir. Exactly. That is why that question. If we go to ocean, do you expect the same kind of bandwidth which you get it into the dashboard? What you are getting?
Not obviously, because in this case, because everything we use was a wide communication, so we get exactly the data we're getting from the AV, for example, 100% of data. But in terms of hydrophones, there are a lot of noises involved. For example, thermal noises from the oceanic shallow water region. All these things need to be considered. But in that case, we are using something called meta-heuristic algorithms, if you heard of it. So it is inspired by animal social behavior. So the professor developed something called meta-heuristic algorithm to remove all these noise resources to efficiently communicate with the ASV using these hydrophones.
Okay, sir. And one more thing, this is my last question. This WiMAX, you told that it will go up to 100 kilometer distance communication. Am I right?
Yes.
With the help of base station attached with the buoy in the sea ocean.
Yes, with a base station attached with the buoy. Otherwise, it cannot go beyond that. And it's
It's
also
only-
power hungry.
It's only in surface.
Yes, it's only surface.
Okay. And will you advise us? Did you advise any researcher to go the proposed model which you tested in the swimming pool model will go for ocean, like a tethered with ASV and AUV?
Yes. Actually, like there is a requirement from NIST Vizag
Okay.
National Institute of Social Sciences. So they have the requirement of using this, combining AUV and ASV to identify the real tracking of AUV, and also NIOT from Chennai, National Institute of Ocean Technology. So they're also actively working on these advanced technologies. But I'm not sure NIOT is currently working on edge computing. But I'm sure NSTL from Vizag, not NIST. It's NSTL from Vizag.
Sure.
So they're actively working on AUVs and also especially the real-time tracking of AUVs, I can say.
Sir,
If you want,
one
I
more
can
la-
connect,
one more last question, sir. Sir, please, this Raspberry Pi used in the AUV, which is only taking the payload data, or it will be used for navigation also? The same Raspberry Pi.
It can also be useful for navigation because Raspberry Pi is being a microprocessor. So we can use the Raspberry Pi for both the navigation and also for,
Sir, do you
getting-
think the volume of data which is coming from different sensors, this Raspberry Pi can able to handle it?
So that's why we are deploying Edge IoT as a service. It's ML inference, so that can filter out all this data and send the required data to the cloud for the processing.
Okay, sir. Okay. Thank you, sir. Thank you.
Thank you, Srinivas.
Yeah. So yeah, next Shambhunath can go up with his question. Hello, Mr. Shambhunath.
Shambhunath ji, can you hear us?
So might be he's not audible from his one. Yeah, Kumar Sita, you can go with your question.
Hi, Sandeep.
Yes.
That's a wonderful presentation. So I have a small doubt actually. Like, as you
Hello,
are
am I audible
teaching
now?
Yes.
Yes, Shambhunath sir, please give us 1 minute.
Yes.
Let the attendee ask the question, then we will move to you.
Okay.
So as like you are showing that digital twin dashboard. So can you tell me that like what is the advantage of using this digital twin technology here over the normal monitoring dashboard?
Well, while we are discussing with the university, they said for the non-technical people, it is very difficult to understand graph-based dashboards. So usually we use digital twins to visually see the virtual kind of instruments. So it is easier for the operators who are working in the industries or some other industries. They can easily visualize and see what is the problem instantaneously. That is a use case of a digital twin that we got from the university.
Okay, thank you.
So it can give instantaneous analysis. For example, if something is wrong with the system, it can instantly display green button to red button in your system or in your whatever virtual you created. That may be AUV or some other industrial instruments.
This also we can show in the dashboard also, right?
Yes, it can be seen.
Okay then. So we can move to Mr. Shambhunath. You can go with your question.
Yes, thank you, Sandeep ji, for the very informative presentation. Actually, I got this link from my colleague, Professor Alokkanti Dev. Okay, so
Okay.
I am working at CMERA Durgapur and heading this underwater robotics group.
Oh.
So probably you know that we have couple of AUVs like 150-meter depth of operation we developed in 2011. Then in 2017 we have developed AUV for which can go up to 500-meter in sea depth.
Okay.
And currently we are working with Deep Ocean Mission for homing and docking system development to charge the to avoid several time launching and retrieval, as well as to charge the vehicle. But that's a very challenging task we are facing.
Okay.
So, I have one whatever digital twin that you have shown already. My colleague Srinivasan, he has some query and some of the questions are already answered. So,
Okay.
how do you feel that in sea environment that will be feasible to track the AUV with that kind of ASB, because the range of operations that are when it is very limited, maybe within 1 kilometer radius, that might be possible. But when a Navy and other defense partners, they are thinking of to deploy autonomous underwater vehicle for 30 days of operation, how that kind of digital twin will be helpful in that purpose.
Okay, so you're talking about 1 kilometers from AUV to ASV or what it
No,
is?
1 kilometer. I am see last in our previous experience, what we used to see that whenever we are deploying our AV from ship, so we used to get maybe RF bandwidth in the range of maybe 500 meter or so on surface communication. Even acoustic bandwidth with some very famous company like Evologics Germany. So they are having that transceiver and transponder. So that also used to get, though they used to say that it is 14 kbps in that range, but we used to get one third of that in real environment. So that these are the constraints. So how will be ensuring that in that kind of sea environment where sea states are not fixed or it is varying. So what is the future of this digital twin? What you have shown in case of
Yes.
sea environment?
Yeah, I can clearly understand the problem because during our brainstorming session, we also found a lot of the challenges, and we have seen there is a huge potential for this edge computing, especially in terms of marine sector, because this is a very niche field. If you see the technological advancements in marine field, for example, AUVs or any other deployable systems, it is not yet updated. So if you want a detailed discussion, I can connect you with one of the professor who is working in NSTL. If that is okay, then I can also share his contact number. Maybe if you also would like to take it offline, we can discuss more on the challenges, how we can take it forward in terms of using edge
Yes,
computing.
sir. Who is that professor? We are in touch with NSTL also.
Okay.
They are that HAUV team or which team you are talking about?
It's an AU team. Like his name is Shashibhushan Rao.
Oh no, I
Okay.
don't know. Okay, maybe we can connect.
Maybe I can connect with you. Yes.
We are in touch with Professor Pushkal Bhattacharya, scientist,
And also another
Dr.
professor,
Dr. H.N. Das.
Okay. Shantos.
So that high endurance AEV that they are developing. Fortunately, I was also a review committee member of that high endurance AEV that NSTL is testing currently.
All right. And there is one guy from like his name is, I remember, Shantos. Yes, MNVSS Shantos.
Santosh Lakshmi?
No, not Shantos. He is Shantos Kumar.
Okay. And Shiju John. Yeah, we know a couple of people earlier. Monu Korela was also there. He is not there now.
So I can share my contact number here. Maybe we can have a chat on this. Yes, this is also my WhatsApp number. You can ping me, then I will directly connect with those people.
Yes, sir. Please repeat your number once again. 8555.
Yes, 8550
Okay, thank you so much.
Thank you. Thank you so much.
So yeah, thank you everyone. So there was a suggestion from everyone to kindly share your PPT if possible over the mail, so I can distribute among them if it's feasible from your end. Kindly.
Yes, sure.
So if it's feasible from your, kindly share it. Also, during the registration when we took a thing, so there was a question from one of the registered member that he wanted to know what's the scope of edge computing. I guess that question was already answered during the session. If there is something else, kindly if you can go forward with the question again.
I can say currently there are a lot of sectors who are trying to involve edge computing, but you can relate edge computing is like a brain, but it is not having the kind of nervous system, I can say, because for edge computing to process efficiently, it requires massive amount of data in which otherwise we cannot harness the real power of it. We can also say edge computing, if you don't integrate all the sensors together with a lot of data, then we can call it as just like a normal cloud computing, right? So now it requires some kind of a support in terms of deploying huge amounts of sensors and huge amounts of data, but that is also very challenging in terms of for example, if you take any power plants or industries, so the way they're using the sensing systems is not scalable, right? So whatever they're buying it in a very expensive manner, and they can only put one device at one place and it is not suitable for edge computing to do the processing, right? So if you place one system at one place, it can only generate few amounts of data or few MBs or GBs of data, which is not suitable for edge computing to power it up. So it requires scalable kind of system, maybe that is in a power plants or maybe in the power stations or power utilities. So I think there is a lot of scope, and I can also quote a lot of examples like how edge computing is being currently used for space applications as well.
Okay, so yeah, I guess that was yeah. So yeah, there was another question in the chat box. So related to IP address assigned to edge devices, can you please share your views? So it was asked by Dr. VDVM. So yes, sir, you can go forward with the answer.
Related to IP addresses assigned to edge devices. Usually, for example, if you are using AWS Green Grass service, so whenever you deploy the AWS Green Grass core onto your core device, for example, in our case, we use Raspberry Pis. Now we can integrate this with other devices. For example, different sensors having different set of unique identity numbers. So here we are not directly using the IP addresses for each of these sensors, but we're using unique identifier numbers. For example, there are 10 sensors in which we are getting this data from 10 sensors. So we should find a way to know which sensor is providing which data. So here we are placing some unique identifiers. And for IP, whenever we are creating the deployment in AWS dashboard, so it will generate the IP, and that can be directly deployed to your Green Grass core software, Green Grass core device, which is Raspberry Pi. So we can also increase the network of these devices. For example, you might have one core device, or you might have multiple core devices, which is gathering data from multiple sensors. So in this case, IP will be an issue because the sensor must know to which core it is actually sending the data to.
Yes. So yeah.
So in this case, we can either generate our own IPs for each system and sync that with the AWS deployment in our cloud environment.
Okay. So I guess that was able to answer your question. Yeah. So I would request everyone to, if it's feasible from your end, kindly on your camera so we can take a small screenshot of the session, kindly. So if everyone can just, if it's feasible from your end, kindly. So okay, Shobhasachita, will you take the screenshot kindly?
Sure, please. I'm taking the screenshot. Okay.
Okay. So is it done, Shobhasachita?
Yes. Thank you very much for turning on your cameras.
Okay, thank you. So also another thank you to Mr. Sandeep Batula. So for your kind words in today's session. Just the last thing, on behalf of everyone, mainly from IEEE's Computer Society Student Branch Chapter, IIT Kharagpur section, I would like to present you today's for your kind words on the given topic. So I will be mailing you the soft copy of this just after the session, if feasible.
Yes.
So yeah, thank you again.
Yes, thank you so much, everyone, and Rasdeep, Kumar, and Sabyasachi sir, and also Devashi sir for joining, and also have a great discussion. Maybe we can connect once offline, discuss. We have a lot of ideas on how we can take this edge computing into the industrial perspective, and we also want to learn and explore from you guys, from your people as well. Yes. So if possible, I will also visit IEEE, CS department personally, and also want to meet you to know your insights on this as well.
Yeah, it will be great. It will be great meeting you as well. Thank you again. So thank you to all the attendees for attending the session. We hope to meet you soon in the next session. Thank you.
Thank you so much, everyone.
Thank you, everyone, for joining the session. Thank you very much.